In this class, we will see about selection of pump. Selection of pump concept is common for both drip irrigation as well as sprinkler irrigation. Before one intends to select a pump, he needs to know two factors. One is what is the pressure head to be developed by the pump, and what is the discharge rate that is expected out of the pump. So these two factors are needed to be known before one attempts to select a pump. The head is also termed as a total dynamic head to be developed by the pump. What is total dynamic head? Total dynamic head is the head to be imparted to the water by the pump so that desired discharge is obtained at all the outlets when sprinkler or drip is in operation. So what does total dynamic head? What are the components of total dynamic head? It's a sum of frictional loss all along the pipes, main, submain, lateral, and the water should also pass through many fittings, fertilizer injection equipments, filters, valves. So head losses that would occur when water goes through these fittings and accessories, and the elevation level difference between water level in the well and centroid of the critical submain or lateral. Critical submain is the critical submain or critical lateral is the one which first shows symptom of failure when there is a small decline in the performance of the pump. So that is the place where you first see the problem of pump. So one should find out the level difference between the centroid of the critical position and also the water level in the well. So that is called elevation head to be developed by the pump maximum. And finally, the pressure heads, those are required at the outlet of the system. If it is drip, we need at least 10 meters. If it is sprinklers, it starts from 20 meters, 30, 40, 50, like that, depending on your system. That has to be substituted. So the steps in finding total dynamic head is: first identify the critical submain and lateral where it is. Find the elevation difference between water level in the well and the critical submain. The critical submain or lateral maybe it is too far from the control head, or it is too high from the control head, or arbitrarily any combination of these things. So in this problem, it is very easy to find out that it is at a largest distance. But in a real life situation wherein the field has lots of undulations and subdivisions and all, one has to sit down and find out where the critical lateral could be. At one stroke, it may not also be possible to find out where the critical lateral will be. Maybe one or two trials by experience, one will be able to find out where could be the critical lateral ease. So the next step is decide the pressure head required at the outlet, compute the friction losses in all pipe sections and fittings and accessories. Finally, if you want to be safe, you add also a factor of safety around 10 to 20% of pipe fitting and frictional losses as miscellaneous losses. Add everything, and you get finally total dynamic head. So this is how one should find out total dynamic head. And for pump selection, you should also know about some basics about pumps. And this would have studied in your pump course that there are different types of impellers. One is this an impeller, this another type of impeller, this another type of impeller. It's a radial flow. In radial flow impellers, water comes axially into the eye, then it turns direction and it moves radially out. So these are called radial flow pumps. And in mixed flow pumps, water comes axially and it goes with an inclination. It goes with an inclination. So with the inclination, one can see a axial component and also a radial component. So since it has both axial and radial components, they are called mixed flow impellers. In axial flow, 100% axial flow is impossible, but 99% we can say. When it is rotating, when the impeller is rotating, it moves, the water moves axially. Water is given only the velocity and it is not given the pressure, but it's 100%. In this drawing, it has been shown as a straight line, but it will also have some kind of an inclination, something like this. So these are all the three basic impeller types. Most of the time, these axial flow pumps are not used for drip and sprinkler irrigation because the head developed by this pump is very low and that may not be sufficient to operate drip and sprinkler irrigation. Most of the time, radial flow and mixed flow pumps are used. So if you recall your pump codes again, for radial flow, the operating characteristics of the pump, the typical operating characteristics of pump I have shown here. So see here, in x-axis discharge rate has been taken. In the y-axis, you take three things: total head, efficiency, and horsepower, shaft horsepower. So this is the total head curve. For radial flow, as discharge rate increases, the head developed by the pump gets it drops down. But in case of radial flow, the drop may not be very high. It is not a steep fall. It is somewhat flatter. And this is the efficiency curve, power efficiency. What are horsepower versus electric power? If you find out the efficiency, then you get efficiency curve. And if you look at the efficiency curve, you should operate or you should select your pump in such a way that you operate near the efficiency point. If you draw a line like this at the efficiency point straight, then you get a discharge rate. That is the design discharge rate for that pump, for these characteristics. For this is the design discharge rate, and correspondingly you get a head. This is the design head. So you should select your pump in such a way that it operates very near to design head and the discharge rate. Only then pump will be operated with your efficiency will be maximum. So this image shows typical characteristics of different types of impellers. So this is for radial flow. I already discussed in previous slide, and this is for mixed flow. This is for mixed flow, and this is for mixed flow propeller pump, axial flow. Propeller pump and axial pumps are synonymously used. If you look at mixed flow pump, two important things you can notice here. The head curve, which drops steeply. You see, it drops steeply. So when you suspect your water level in the well to fluctuate to a higher degree, then better not to go for a mixed flow, because if head variation is more, if head variation is more, the discharge will also get very much affected. But in case of radial flow pumps, if the head variation exists, then discharge variation may not be very high. One more thing you can notice here is the power. Power curve is approximately same, and that too near the maximum efficiency point. You see, it is almost flat. So whatever be the discharge, whatever be the even sometimes when during monsoon seasons, if the water level in the well rises up, then you will be operating at a very low head. At low head, the discharge will be more. In that case, if the discharge is more, here the power output will not get changed. Same is the case when discharge gets reduced also. But look here, in case of radial flow pumps, if the water level in the well is lower, then when discharge is higher, what happens to the power? Power keeps on increasing. So that is the reason why many times what do you call your electrical winding would get burnt when water level in the well is at a higher elevation. When water level is not too deep, your pump will not get, your electric winding will not get burnt. But when water level is at a shallow depth during monsoon, you will find that it will operate at a lower head but higher discharge, and during that time power will be more, power consumed will be more, and there is possibility that the electrical winding may take more current and it may get burnt. So these are all some of the basic issues about pump hydraulics that should be kept in mind while selecting a pump for your system. So I said that mixed flow propeller pumps, axial flow propeller pumps are not very much used for drip and sprinkler irrigation, but you can also recall how the power input and head curve appears. You see, when you decrease the discharge, the power consumption goes infinite. The head produce also, it goes infinite, and there is possibility of even pump bursting. So, and not because of this reason for sprinkler and drip irrigation these pumps are not used. It is because the head developed by the propeller pumps are not sufficient to operate drip and sprinkler irrigation. So this is one basic issue, basic subject. I would like to recall what do you understand from the term evaporation. So if you take a still water, when water particles gain energy, then it would rise up and it will become a vapor. So when water particles get energy to get away from the liquid mass, then you call that process is called evaporation. So how to give energy to water particles to get away from the liquid mass? One is if you add heat to liquid, you add energy, then its vibration is sufficient to detach from the liquid mass and to get away. This is what is the process of evaporation. Most of the time when we say evaporation, we recall only this thing, giving heat to water and making the water particle to evaporate. But in thermodynamics, we would have studied this is not the only way of water getting evaporated. And let us take a closed container in which the container is capable of conducting heat, and it is placed in a normal place, in a normal atmospheric pressure. So if the surface is covered, then there is no water vapor here. So this is a empty space. So if I remove the flat surface, then what happens? Heat energy gets absorbed by the container, and gradually there is a evaporation, and also condensation would also simultaneously occur. But evaporation rate will be to start with, it will be higher, and condensation will be smaller. Then after some time, both will become equilibrium, and at the equilibrium you will have a kind of water vapor, and you will have a vapor pressure that would exist at this place. At that vapor pressure, the evaporation rate and the condensation rate becomes equal, or you can say that evaporation does not occur. Net evaporation does not occur. So this is the basic thermodynamics we all have studied. But you extend this thermodynamics concept now by just imagine that the container is this volume is increased. Its volume is increased, and you don't allow anything to come inside. So what you are doing in nutshell, if you are increasing the volume, you are decreasing the pressure. If you keep on decreasing the pressure, what will happen is the same mass has to occupy in the increased volume. What will happen is everything will get evaporated. So by decreasing the pressure, also you can make the water to evaporate. So that is what is the concept I wanted to drive in your mind with this slide. So if water pressure drops down below 0.24 meters of water column, so that is what is called 0.24 meters of water column here. This is the saturation vapor pressure. If water pressure drops down below 0.24 meters of water column at 20 degrees centigrade, that's what is the standard. There will be flash evaporation. Everything will immediately get evaporated. So if the pressure is in absolute terms, 0.24 meters in absolute terms, if the pressure is more, say 0.3 or 0.4, then also evaporation will be there. Okay. So more closer to this value, more will be the evaporation. So this should be recalled. All these knowledge you would have studied in basic thermodynamic courses and in chemistry, in all other places. So next concept is net positive suction head. What is net positive suction head? You know that at the eye of the pump is the place where the pressure of water is the lowest. So net positive suction head is the pressure head at the eye of the pump minus vapor pressure of water. So it means that above vapor pressure, how much pressure of water exists at the eye. So this is called net positive suction. So higher the net positive suction, it is better. So this is what is the basic concept of net positive section. For net positive section, based on this formula, by applying Bernoulli's theorem between your pressure head measurement at delivery at section pipe using the values of delivery lift and friction loss in the section, you can derive this equation. It's very simple, and the derivation is given in our manual. So one can calculate net positive section head. What do manufacturers do is, for each pump, they calculate NPSH required for the pump, and they give in the label. Net positive section head required is calculated, and that is given. So what we should do is, for our site conditions, we should also calculate net positive section. Our calculated net positive section head for our site should be greater than the net positive section head recommended by the manufacturer. Only if our net positive section head in our site condition is more, then our pump will work. Or otherwise the drop in the pressure at I would be more than the vapor pressure of the water, and pump will not function. So this should be kept in mind. So when you are selecting the pump, these factors should also be considered. For pump selection, the pump selection charts, those are supplied by the manufacturers, are mostly used. This is a typical chart. To start with, in the first page of the catalog, you will find this kind of charts. This relates to on the x-axis discharge rate, on y-axis the pressure head to be developed. So for your discharge and for your needed pressure head, you get a point, and these here you find values, and these are all the individual group of pumps. So here somewhere 80 to 200, like that it is given. So 80 to 200, for 80 to 200, that can be a model or a HP or anything. It's a code. For 80 to 200, you will have a separate detailed characteristics, something like this. See here, it has a head versus discharge rate curves, and also you find ISO efficiency curves. Okay, ISO efficiency curves. So 80. So you find here at the center, if you come, so along this way, if you come, this is the line of maximum efficiency. Okay, and next curve is net positive section head. This is the required net positive section head versus discharge rate. And finally, power for different impeller diameters, what is the power. So this is how it is given. So what do you do is, you again use your discharge rate here and go up and select. You go very near here along this is the maximum efficiency path. So let us say here you get a point, then let us say your head is somewhere here, then you get a point here, and correspondingly you find what is the NPSH required, and see in your site condition whether that much amount of NPSH can be obtained, and also you can get the power also from here. So power, horsepower or power in terms of kilowatts you get. So that can be used for the purchase of the pump. So this is a procedure. Normally has to be done by an engineer. If you know this, then your value will be better. An engineer's value will be better. Either you practice processing engineering or soil water or energy or farm machinery, anything. If you are able to select a pump optimally, then you will be valued as a good engineer, because the use of the pump is everywhere. So this is a very important concept you should keep in your mind. So let us do a small simple problem in which the pump suction and delivery pipe length is 5 meters. Okay, and you have decided the diameter of the pipe in suction is 65.6 mm, and you have one foot valve, and the design discharge rate you obtained is 8 liters per second, and in the control head, inside diameter of pipe and all the accessories are 79 mm, pipe length is 10 meters, you have one reflex valve, and you take a decision that filter will be cleaned when pressure differential between inlet and outlet is 2 meters, and you also have 2 butterfly valves. And in your main, submain and laterals, the data goes like this. Main pipe has a provision for 14 laterals with 14 T's. At a time, 2 laterals can be operated. One lateral discharge rate is 4 liters per second with 10 sprinklers in each lateral. Lateral length is 120 meters. Lateral diameter is 68.6 millimeters. Your main has six butterfly valves. Length of main pipe is 210 meters. Diameter of the main pipe is 82.4 millimeters. Spacing between laterals is 15 meters. Pressure head required at the sprinkler head is 25 meters. Elevation difference between water level in well and the centroid of the critical location is also 25 meters. So this is the data for which we will select a. So how do we do this? So you need to calculate the pressure head losses. So for pump suction and control head pipe and main pipe friction losses, it is going to carry 8 liters per second, and for each length calculate this blind pipe formula, find out friction losses. For submain pipe, find out the average losses using inverse friction factor. For submain and lateral, find out the average friction loss. Then you get the total friction loss in the pipe. Similarly, fittings. You have foot valve, reflex valves, butterfly valves. These numbers are also given, and these are called minor losses. And this formula has been derived in your manual to find out minor losses from the formula K into V squared by 2G gets converted into this way for this unit system. So you calculate the head losses, add this loss and this loss put together. Total dynamic head is friction loss, fitting loss, then elevation loss, friction loss, fitting loss, then elevation head 25 meters, riser height is 2 meters, let us assume. Then plus 25, and I do not know why I have put this 1. To look into your manual, so I do not know for what purpose this 1 has come. And total dynamic head you get is 65.44 meters. So what you need to do is for 65.44 meters head and 8 LPS discharge, you have to select a pump. So previously I showed this kind of a catalog, and now I am showing another kind of a catalog where things are just shown with a tabulation. See here for 8 LPS. So this is the maximum efficiency column. So for 8 LPS it is nearby 8 LPS. See here liters per second 8 LPS, and head developed is here. Head developed is near 65. So 66.5. So see here. So you can purchase this pump. 7.5 kilowatts 10 HP. This model. So this is the way one should select the pump.